on this computer. Okay, so sorry for the delay in starting. Got a little distracted. So we were talking about exactness in differential equations. And let me grab my coffee. I had a nosebleed today, so it's not serious, all this blood. Let me get rid of these things also. So let's see, I hope people can see the screen.
We cannot see the screen right now.
You cannot see it?
No, we can't.
Oh, Christ, what did I do? All right, I just do not know what, apparently I clicked in the wrong place somewhere and that, aha, wait a minute, no, that's not it. Okay, if anybody has a good idea, do shout it out. All right, here, share screen. There we go. All right, with luck, you can see the screen now, is that right?
Yes, we can see it now.
Okay, all right, sorry for the confusion. So we were talking about exact first order differential equations, and basically it's that a differential is exact if it's the differential of something. So in other words, if p dx plus q dy is d phi, then that's an exact differential, and then d phi, of course, will be phi, the x derivative of phi times dx plus the y derivative of phi times dy. And an exact differential equation then is when you set this exact differential equal to 0. And in such an, if you have then an exact differential equation, then you have that p is the partial of something, which I called phi with respect to x, q is the partial of something I called phi with respect to y, and then since phi is a function of x and y, the y derivative of p is the yx derivative of phi, which is also the xy derivative of phi, which is the x derivative of q, q being the y derivative of phi. This is called the condition of integrability, and it implies that the ODE is exact and integrable, and we'll see an example later. A first order ODE that's separable, and separate is exact because the y derivative of p is equal to the q derivative, the x derivative of q, because both derivatives vanish. So there are a couple of examples. I don't know if we need to go through them in detail. The meaning of exactness, well, if you have an exact differential equation, then this left-hand side is the differential of something, and the differential equation says that the differential, that the something is a constant and has no vanishing differential everywhere. In any case, if this differential is exact, then it's so there's the distinction here between an exact differential, which means that p dx plus q dy is the differential of something, which I called phi, and an exact differential equation, which is setting that differential equal to 0. So if we then, by the way, this is called the exterior derivative of phi, p dx plus q dy. If the thing is exact. So this would be phi sub x dx plus phi sub y dy. In any event, the point is that you can integrate, in general, if you just have two functions, p and q, and you integrate along a contour, you get a function that depends upon the endpoints and upon the contour. But if the differential is exact, then it depends only on the endpoints. And in that case, one can integrate along any contour, and what we get is phi at one end minus phi at the other end. And that defines then a function that's independent of the contour. If then we set that differential equal to 0, what we get is that phi of xy minus phi of x0, y0 has to be 0. And in that case, and that's because phi is a constant, so d phi is equal to 0. And then in that case, we could solve this equation. If we integrate it, we'd integrate this thing along some contour, it doesn't matter, and we'd be able to solve for y of x. This is a general example on the use of exactness. I think it would be useful pedagogically to skip to a particular example. So here we've got a differential and that's exact, and the exact differential equation is that the differential is equal to 0, and here p is log of y squared plus 1, and q is 2y x minus 1 over y squared plus 1. So the y derivative of p is just the y derivative of that, and it's this. The x derivative of q is the same thing. And so what can we do? What we can say here is then that phi sub x is p, and so we integrate in the x direction. We integrate p in the x direction, and we get phi of xy then is the integral of this plus c of y, and that's just x times log of y squared plus 1 plus c of y. Then we use the fact that the y derivative of phi is q, so the y derivative of that, we differentiate this and we get that. But on the other hand, that's q, and we know what q is, it's this thing here. And so we set all these things equal, and we find that the y derivative of c is this. Then we integrate c in the y direction and get c of y equal to minus log of y squared plus 1 plus d. Now that we've got c of y, we can go back to this equation and substitute for c. Then we get that phi is equal to x minus 1 times log of y squared plus 1 plus d. And now what we do is we set that phi equal to a constant. So we set x minus 1 plus log of y squared plus 1 plus d equal to e, or equivalently set f equal to e minus d, and then we can unravel that and solve for y. And that's the solution then of the original exact differential equation. So basically, if the differential equation is exact, you can then solve it. The general description was over here, namely that P is the x derivative of phi, Q is the y derivative of phi. And the differential equation then is such that we know that phi is the integral of its x derivative plus something that depends upon y. We do that integral knowing what p is, and we get phi is equal to r, which we know, and c is arbitrary. But then q, which we're given, we know that's the y derivative of phi, but that's the y derivative of r, which we now have, and then the y derivative of c, which we still don't understand. But we then have that the y derivative of c is q minus the y derivative of r, which we know. So we integrate what we know on y and then add a constant of integration. So now we have calculated c in terms of things that we know and an arbitrary constant. We can then put c into the function r plus c, which is this equation here. And we then set phi equal to e, and we get this expression, r plus c is equal to r plus the integral of q minus the y derivative of r plus d is equal to e. So this basically is the solution. And now let's remember what r was. R was the integral of p with respect to x. And okay, so that means if the thing's exact, you can solve it. Let me, in the examples chapter, I've added an example, and because there's a connection between exactness and analyticity. So let's jump over to here. This is new stuff, not in the book, but it'll be on the web in examples on the web page. Excuse me. So the basic thing is that a differential is exact if it's the change dg in some function. Let's see, I can make this bigger and you guys can, I guess, see it better. Suppose f is u plus iv, both being all three being functions of x and y. Then df is du plus I dv, and we can write du is ux dx plus uy dy plus I. dv is vx dx plus vy dy. If further df is proportional to dz, then we can write this, that df is something u plus iv times dx plus I dy. And if we multiply that out, we get this. So now if we compare these two expressions, what we have is that u here, which is the coefficient of dx and the real part of the coefficient of dx, well, that's ux, and then v is the dy, but the real part, so that's minus uy. And on the other hand, v is also equal to v sub x, and u, which occurs here, is also v sub y. Now we notice that we've got some striking regularity here, namely u sub x is v sub y, and v sub x is minus u sub y. Moreover, we also can notice that if we take the y derivative of u, that's the y derivative of u is u x y. That's the same thing as minus the x derivative of v. So that's this. And then the y derivative of v is vxy, and that is the x derivative of u. So we get these two equations, or these two pairs of equations. But these are the Cauchy-Riemann equations. The first set are the Cauchy-Riemann equations for f. And the second set are the Cauchy-Riemann equations for the derivative of f, which is u plus iv. And so what we have, what we learn from this basically is that all integrals of an analytic function and all derivatives of an analytic function, a function that's analytic in a simply connected region, are analytic in that simply connected region. And so so you can infinitely integrate and infinitely differentiate an analytic function, and you get, you keep getting functions that are analytic. When I say when I say integrate the function, I mean integrate along a contour. And since the integral is it depends only on the endpoints, we're actually defining a function. So that is, now let's see, where is my chat thing? All right, I think we lost chat. So let me go over here and grab chat. Okay, all right. So if somebody has a question, give me the question. If not, let's go to the next topic here. But actually, I'm sort of freezing, so I'm going to grab a sweatshirt. Hold on. I've got a swamp cooler that is a little too big for the house, and it's great in the month of, say, July, but it's more than one needs in October. Okay, let's look at this topic of integrating factors. And the idea is that you can, if you have a differential equation, you can and it's not exact, or you don't know if it's exact. Well, let's say it's not exact. You can sometimes invent an integrating factor, that's to say a function such that if you multiply the whole differential by that integrating factor, say alpha, then you get alpha p dx plus alpha q dy, and that actually is the differential of something. And so the equation becomes integrable. So so the criteria then are that alpha p is the x derivative of something and alpha q is the y derivative of something. But then the y derivative of alpha p is the xy derivative of something, which then is the x derivative of alpha q. And a couple of trivial examples are that the ODE y dx minus x dy equal to 0 is not exact, but if you multiply by 1 over x squared, you get this expression. P is then minus y over x squared, q is 1 over x, and you get that p sub y is equal to q of x. Another integrating factor is 1 over xy. 1 over xy, and then you get dx over x is dy over y, and there it's exact because p is a function of x, q is a function of y now, or alpha p is a function of x, alpha q is a function of y, so py equals 0 equals qx. So these were somewhat trivial things, trivial examples. But basically, if your differential equation is exact, then you can solve it. If it's not exact, sometimes you can turn it into a differential equation that it's exact. And but on the other hand, a first order differential equation is by no means hopeless, as long as it's well, it's often soluble. I mean, let me not try to speak with great generality. The next topic is homogeneous functions, and this is important in physics as well as mathematics, and probably important in engineering. A function of, say, k variables is homogeneous of degree n if you multiply all of the individual variables by the same number t. What you get is t to the n times f of the variables without any change. An example, z squared log of x over y, homogeneous of degree 2 because ty, what you get is ty squared log tx over ty, the t's cancel, and you get t squared z squared log of x over y, so it's homogeneous of degree 2. Now, Euler, who invented so many things, noticed that if you take this definition here and differentiate it, you differentiate f of tx with respect to t, you get partial of f of tx with respect to t, the first variable, which is tx, well, the ith variable, which is txi, and then the derivative of txi with respect to t. That's xi times the derivative of tx with respect to txi. On the other hand, if you write, if f is homogeneous with degree n, then f of tx is just t to the n f of x, and ddt of that is n t to the n minus 1 f of x. I'm using x as shorthand for x1 dot 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 xk. So now we have this equation here, and now in this equation we set t equal to 1, and we get this equation here. The t goes just replaced by 1, and we get the sum over all k variables of the ith variable times the derivative of the function with respect to the ith variables, n times the function. And that's true if f is homogeneous of degree n. There are many examples and uses of this in physics, and because these examples are physical, I think it's particularly worth going through some of them. So the internal energy is a first degree homogeneous function of the entropy, the volume, and the number nj of molecules of kind j. And the reason is that if you multiply the entropy, the volume, and the numbers of particles by t, what you're describing is t sample t. Well, you're stretching the whole system by t, so the internal energy goes up by t. And on the other hand, the derivatives of the internal energy with respect to each of these variables are defined as, with the others held constant, which is what we mean by a partial derivative, are defined as the temperature, and we have a minus sign for the pressure, and then this is the chemical potential. And consequently, Euler's theorem tells us that this sum, and we get a minus sign because we stuck a minus sign in here. Sometimes conventions in physics just make things more complicated down the road. Anyway, we then get this thing here is the right-hand side, and for n equal to 1, we get u, which is the left-hand side. Just to switch to cosmology for a second, if the energy density of empty space is positive, then the internal energy of the universe rises as the universe expands. Thus, dark energy creates negative pressure which accelerates the expansion of the universe. So the simplest way of thinking about dark energy is that empty space, or that something, quantum field theory or something better, describes nature, and in particular describes empty space. And you can imagine the Hamiltonian of quantum field theory, or some better theory, having a ground state, and that the ground state energy is proportional to the volume, and the ground state energy density is non-zero, and in fact it's some small positive number. And that's something that was discovered, I don't know, 20, 30 years ago. Anyway, since du is this, we can form an expression for the change in the entropy, and we get this expression, and that leads to a bunch of definitions that are like these definitions of 1 over inverse temperatures, the partial of entropy with respect to internal energy, and so forth. On the other hand, entropy is not a homogeneous function of the internal energy, the volume, and the various numbers of particles. Whoops, we've got some serious questions here. Right, so one person asked, what about homogeneity? Is it possible that when you did this expression, you'd get some terms that were homogeneous of degree 1, others homogeneous of degree 2? Yeah, that's the general situation. And then you don't get Euler's theorem. There's probably some other theorem, but it's not as convenient. Right, okay, so I think the chat person was just raising a valid point. And an example of that is the entropy, which is not a homogeneous function of these variables. In fact, one could multiply u, v, and n by t and see what happens. Little t, not the temperature. What you'd get would not be t to the n times the entropy. There is a formula for the entropy of the ideal gas due to Sakura and Tetrode, and that is, it's an approximate formula and for an ideal gas, and quite surprisingly, it involves Planck's constant, h, as well as the mass of a molecule of the gas. So I will not go off on a tangent on this. Let's go to the next topic, which is an application of Euler's theorem, namely the Virial theorem, which of course is important in mechanics and in astronomy and I guess cosmology as well. So let's imagine n particles moving non-relativistically in a potential of 3n variables, the 3n coordinates, because it's three-dimensional space. And imagine that the potential is homogeneous of degree n. And we'll see some examples in a moment that's a common feature of physics. And in fact, when you have something that's homogeneous, it's normally related to a symmetry. And symmetry is our friend, really. Or symmetries are our friends, because when there's a symmetry, the problem is simpler. Nice things happen. And when there's no symmetry, then we say the problem is cockeyed, and it's not much fun. Anyhow, So what is the virial? The virial is defined as this particular expression. This again is non-relativistic. You sum over all the coordinates, the 3n coordinates, x, y, z for particle 1, x, y, z for particle 2, and so forth. And you sum xi, pi for all the variables, and that's called the virial G. Probably should have called it V, but then we have the potential. Anyway, G. In terms of the non-relativistic kinetic energy, which is V1, P1 plus dot, 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 V, the product of basically V dot P divided by 2, then, and the force, which is Pi dot, the time derivative of the virial is where you differentiate, you take the time derivative of xi, you get Vi times Pi, and then you have xi times the time derivative of Pi, which is F, so you get this. And now, what is that? Well, this here, you can see, is twice the kinetic energy, the non-relativistic kinetic energy, and then what's left over is this term here. And now what we do is we take an infinite time average of this equation. And so that's, what does that mean? That means that if we integrate from 0 to little t, I probably should have used capital T. So let me make a note to myself. So this is the integral of the derivative of the virial from 0 to some large time, and then divided by the large time. Well, that is the virial at a large time minus the virial at time 0 divided by the large time. On the other hand, if these particles are bounded by the potential into some finite region, and they have sort of finite energy and so forth, so that their virial is finite, then since the virial is always finite, as t goes to infinity, we get that this all is equal to 0. And that then gives us this expression here, namely that the time average of the, well, that's why I didn't use capital T. The time average of the non-relativistic kinetic energy times 2 plus the time average of x dot f vanishes. And now again, we're non-relativistic, so we use Newton's law for Fi, partial of V, partial Xi. And we get this this thing becomes that. And now we use Euler's theorem, and we assume that if V is a homogeneous function of degree n, then the sum of the sum of xi partial V partial xi is n times the potential n times V. And so we get the rule 2t is nv, or t is n over 2 times v. So that means that the long time average of the non-relativistic kinetic energy of particles with a bounded virial is equal to, in a homogeneous potential of degree n, is n over 2 times the long-term time average of the potential. Well, that's a very long sentence. Let's do a couple of examples. Suppose we have a gravitational or electrostatic potential that's homogeneous of degree -1. And maybe here I should take advantage of the iPad to, so let me say what we've got here. If we have V is equal to -1 over R, or actually, let's see, do I have minus sign? I think I just have 1 over R, plus 1 over R. But this is 1 over the square root of x1 squared plus x2 squared plus x3 squared. So partial v, I'm sorry, I didn't even need to do that. So let me undo those last things. So v of tx, what will that be? That'll be 1 over the square root of t squared times x squared. And so that's just 1 over t times v of x. So that's t to the minus 1 v of x. So this is homogeneous degree minus 1. And what does that tell us then? That says then that the mean value, the long-term time average of the non-relativistic kinetic energy is minus a half times the long-term time average of 1 over r in this case. Dark matter, well, Zwicky back in 33 of the last century, which is almost, well, it's 87 years ago, more or less, applied the gravitational version of the Virial Theorem to the galaxies of the Coma cluster and used his observation of the luminosities to estimate the gravitational term and found it to be much less than the mean kinetic energy. And he called the transparent mass dark matter. It's unfortunate that he used the term, I guess, dunkel, I think it's German for dark, anyway, and then it became, it stuck. And so we now are stuck with the term dark matter. We should be calling it invisible matter. This was something that someone at Harvard, one of the, in fact, well, anyway, I'm terrible with names. Somebody at Harvard, rather a female professor at Harvard pointed that out in one of her talks. Anyway, harmonic forces. Well, a harmonic potential, so let me switch colors maybe. If we have V equal to a sum of masses times omega squared times rk squared, then, so V of r, then V of tr is, of course, then t squared V of r. So this is homogeneous degree 2. And so then what you have is that the long-term time average is simply equal to the long-term time average of the potential. Notice that in this case, one does, the minus term survives, and that means that the kinetic energy is minus the potential. Of course, in this case, the potential has to be negative, so the gravitational potential energy is well, big mistake here. Let me go back here then and bring out my eraser here and change this to, oh God, I screwed up. I've made this, let's see, can I, oh God. These touch screens are great unless you touch them by mistake. So let me put in Jesus. This is a real pain in the ass. Excuse my Greek. All right, so let me somehow put a minus sign here. Boy, I can't even do that. Maybe the thing to do is to get out of pencil mode and come back in. So now I come back in and boy, I do not know why. I don't, all right, now I'm going to try to, damn it, I now have the wrong, I've got the wrong kind. Well, let's see, maybe this works. No, this is giving me this stupid, pencil settings. Oh, Christ. All right, I think maybe I go back here and double tap. Well, that might do it. No. Well, I don't know. It's very, very, very awkward. So I think I'll stop using the iPad for the moment, because once it switches to invisible writing, it becomes useless. All right, well, in any event, I think we covered that. Let's go to another topic here, which is Legendre's transform. By the way, it's really striking how many of the advances were made by people who were either German or French. The English didn't have a great deal to say at this time during those centuries, apparently. And anyway, the change in, let's suppose A is a function of two independent variables, X and Y. Change in A is D, the A derivative, X derivative of A plus the Y derivative of A times one times dx, the other times dy. But now we can define a new variable as V as partial of A partial Y, and a new function B as A minus Vy. So then if you take dB and you just follow this, it's I should have used the subscript notation. It would have made things a lot easier to read. So this is A sub x dx plus A sub y dy minus V minus dV times y minus A sub y dy. And now you see these two terms cancel, and we just get this expression. So this tells us that B is in effect a function of X and V. But on the other hand, to really make it a function of X and V, we need to use this formula to express Y as a function of X. So in other words, we have to invert this expression. This is partial of AXY with respect to Y is V, and we want to then solve for Y in terms of V and X, and then get rid of Y here. And if we do that, then we have a real expression for B as a function of X and V, namely B is A of Y of X and V minus V Y of X and V. We could, though, go back to A and define a new variable u as a sub x and a new function c as a minus ux. Then dc turns out to just involve dy and du. So c is a function of u and y. But in order to really carry that out, we need to solve for x and solve this equation for x in terms of u and y. And if we do that, we then get c of u and y is a of x of u and y minus u x of u and y. And you can combine the two, and then you get d is a minus ux minus vy. The differential is involves du and dv, so d is a function of u and v, but you then have to solve these two equations so that you get d as really a function of u and v. Now in physics, this actually is quite important because, and it crops up more than one would think, although in elementary textbook examples, you don't see it because people don't want to get, thanks for the suggestion, Senator Udall. I didn't see it in time. Anyhow, this occurs with Lagrangians and Hamiltonians. So suppose we have a Lagrangian. Lagrangian is really an action density. The time integral of the Lagrangian is the action of a process. The differential of the Lagrangian is partial L partial Q dq plus partial L partial Q dot dq dot. And what you often do in mechanics is you set P equal to partial L partial Q dot and define the Hamiltonian this way. Here that we put in an overall minus sign. So instead of writing L minus PQ dot, we wrote PQ dot minus L. This is to get to make the energy positive. What happens then? What's the change in H? Well, DH then is P dq dot plus Q dot dP minus DL. So that's, but P is partial L partial Q dot. And then dl is partial L partial Q dq minus partial L partial Q dot dq dot. And now you see that this term cancels that term. So we just have Q dot dP minus partial L partial Q dq. So the Hamiltonian is really a function of P and Q. But it's not really a function of P and Q unless we take this expression and solve for Q dot in terms of P and Q. So if we can do that and solve for Q dot as a function of P and Q, then we can take this expression and we have here then Q dot, we express Q dot in terms of P and Q, Q dot in terms of P and Q, then the Hamiltonian is a function of P and Q. Now, in typical textbook cases, this is trivial. Harmonic oscillator, this is the Lagrangian. The momentum is the derivative of the Lagrangian with respect to Q dot. We just get MQ dot. Well, Q dot is just P over M, so this is trivial. And we then define H as PQ dot minus L. We just get this expression here. And so this is subtracting L, this is PQ dot. And now we then set Q dot equal to P over M. And so we get this term minus that term plus that term, and we get the usual formula for the energy, the Hamiltonian of a harmonic oscillator. You can also go from the Hamiltonian to the Lagrangian, and you define Q dot as partial H partial P as a definition. You then set L as PQ dot minus H, again, an overall minus sign. And then dl is dq dot plus dq. So L is a function of Q and Q dot. Some thermodynamic examples: the internal energy varies with the entropy, volume, and numbers of particles like this. And so then it's a function of S, V, and N, but we can change the independent variables. For example, we get to the enthalpy by adding PV to U, then DH involves SP and N. So it's a function of SP and N. The Gibbs free energy then is U plus PV minus TS. That turns out to be the enthalpy minus TS. The differential is then dP, involves dP, dt, and dN. So it's a function of P, T, and the N's. But again, you have to actually solve you have to express everything properly in terms of P, T, and N. The Helmholtz free energy is U minus TS, and it looks like that. Okay, so those are some examples. Another example of related issues, differentials, and so forth, is the principle of stationary action in mechanics. This, of course, is tremendously important. The action, as I said, is the integral of the Lagrangian over time. And so what is useful is to look at the change in the action if you change the process. This is a process of Q of T, Q being several variables. So change the process, Q goes to Q plus delta Q. And what's the first order change in the action? Well, it's partial L partial QI, the change in QI, plus partial L partial QI dot, change in QI dot. The change in QI dot is the time derivative of QI plus delta QI minus the time derivative of QI, and that's the time derivative of delta QI. And so substituting this for that, for this, we get this expression here. And now we integrate by parts, and we get an integral over the time involving the small change. This is first order, obviously, so this only works. This is in the limit of arbitrarily small changes in the process. And then we have the endpoints, and the endpoints are partial L partial Q dot, this term, times the change in the Q coordinates, but evaluated at the endpoints. So this is the nice expression where we haven't dropped anything. The principle of stationary action then says, okay, forget about the end terms, only consider changes in the process that go from the same initial point, Q1, to the same initial point, Q2. In other words, the change in the coordinates, you keep the endpoints of the process fixed. You don't vary them. You just vary how you get from start to finish. In that case, the principle of stationary action says that the first order change in the action for small variations of the process that don't change the endpoints vanishes. And that means then, in other words, for an arbitrary infinitesimal change in the process vanishing at the endpoints, we get that the coefficient of delta Q has to vanish. And that gives us Lagrange's equations, where we normally put in another minus sign and write it as d by dt of partial L partial q dot is equal to partial L partial qi for the three n variables. An important special case is when the Lagrangian does not depend explicitly upon the time. And these are called then autonomous systems. And this, of course, is the case that we consider most often in mechanics classes. So in that case, the energy is conserved. And the reason is, well, first of all, we define the energy as PQ dot minus L, and P, of course, is partial L partial QI dot is the PI. So what is the time derivative then of the energy? Well, the time derivative of the energy then is the time derivative of the first term times Q dot see, this is just a little, well, that made it much too small. So it's the partial, it's the time derivative of the first term times the second plus the first term times the time derivative of the second minus the time derivative of the last term. On the other hand, because the partial derivative of the Lagrangian with respect to time vanishes, this thing then is the total derivative, and we're subtracting the total derivative, and we just get L dot minus L. I think there was a typo. Well, actually, there wasn't a typo, but what I wrote in the book was okay. I think it's maybe a little bit easier to write it, to think of it this way. Anyway, it's, God, I certainly didn't mean to have that. All right, I've got a LaTeX error here. In any event, what we get is the time derivative of the energy is 0. So the bottom line is, if you have an action, if you have a Lagrangian that is time independent, the energy is conserved, and this is why. The momentum is canonically conjugate to the coordinates, and if we can write the time derivatives of the coordinates in terms of the coordinates and the momenta, then of course we can do this Legendre transform, which we were talking about earlier. H then is PQI dot minus L. This again is easy when the Lagrangian is quadratic in the velocities, but not otherwise. Another way of thinking of all of this is to say that the change in the action is partial L partial QI dot change in QI. So here we're doing a tiny detour that differs from 0 only at T2. So in that case, it's just PI, I'm sorry, the action is of course, the integral of L. And so it's it's partial L partial QI dot times the change of QI at time T. This is what I'm using here is this formula here. So the change in the action, if we obey Lagrange's equations, these being Lagrange's equations, of course, if we obey Lagrange's equations and don't vary Q at T1, but only at T2, what we get is this last expression. And so what we have is the change of the action is then this, which was what I showed you before. And these are the momenta. So it's the momenta times the change in the final positions. And that tells us then that the derivative, the partial derivative of the action with respect to the final coordinates are the momenta. And so that's a nice expression. We can also write the total time derivative of the action, which is a Lagrangian, in terms of the 3n momenta this way. This is the partial derivative of L with respect to t plus the derivative with respect to the coordinates times the velocities, and that gives us this expression, which is L minus this sum, or equivalently, it's minus the Hamiltonian. So the partial derivative of the action with respect to time is minus the Hamiltonian. Let's see, that was a little fast, I guess. Maybe I should go back again. So let's maybe go over this again, because we've got about 12 minutes left. So the total change, the total derivative of the action is the Lagrangian. And we can think of the total derivative of the action as a partial derivative plus the partial derivatives of the action with respect to the coordinates times the time derivatives of the coordinates. And here we're thinking of the action defined in as the time integral of the Lagrangian from a starting point to an ending point. So what we have is the initial coordinates and time, the final coordinates and time. That's why we have this expression. And so this we've just seen is the momenta. So it's ds dt is partial s partial t plus the sum of the momenta times the velocities. And that tells us then that partial s partial t is L minus this, which then we can recognize as, let's see, where's our expression for E? E was the momenta times the velocities. Right, there's a typo here. This should have a dot. So there's a typo in 7.1. There should be a dot on this. I can, in fact, fit it in real time, I think. Except that I've got a typo somewhere else. So let me just get rid of that. But okay, now this looks a lot more, that now we can identify H as pi qi dot minus L. So that's where the rest of this is. Okay, so now the next topic is the relationship between symmetries and conserved quantities. So as I said earlier, symmetries make problems much easier to solve and to understand and to visualize. They have another benefit, which is that symmetries lead to conserved quantities. So to see this, let's consider a change in the coordinates, a small change in the coordinates, which means that we have a small change in the velocities. We call this a symmetry if there's no change in the Lagrangian. So partial L partial qi dqi plus partial L partial qi dot dqi dot equals 0. If we now write this as Lagrange's equations, in terms of Lagrange's equations, we'll see that Q is conserved. Q here is, it's the momenta times the change in the coordinates due to the symmetry transformation. So delta Q, so in other words, we have a symmetry transformation, delta Qi of t, and so at any moment in time, Q is this thing, where there's delta Q. So we take the time derivative of that, we get the time derivative of the first term times the second plus the first times the time derivative of the second. By Lagrange's equation, this is just that, and then this is that. And so what is this? Well, this is just the statement that that this quantity vanishes. And so this here, let's see. The point is that you see this is just DL, and we just said that DL vanished. So this is so because DL vanishes, which is the symmetry condition, the time derivative of Q vanishes. All right, so let me try to restate this. If you have a symmetry defined this way, then DL defined this way vanishes, and this quantity, Q, which is the momenta times the changes in coordinates associated with the symmetry, is conserved. So I think we need a couple of examples. Emmy Noether was the first person to understand this very important and very general property of classical mechanics, classical field theory, quantum field theory. Of course, I guess she understood it in terms of quantum field theory because she lived into the age of quantum field theory. So so let's look at Noether's theorem for momentum and angular momentum. So suppose the coordinates or the Q's are the spatial coordinates of some system with these time derivatives, and suppose the Lagrangian is unchanged by a spatial displacement, also called a translation, by some constant vector, ABC. So dQi, dXi is A, dYi B, dZi C. Then the momentum in the direction D is conserved. P dot D is conserved. So this is the quantity that's conserved. So this is Q. What is this P? Well, you're instructed to take the partial of L with respect to each velocity and dot it into the symmetry change. The change in the delta is the change in QIs under which the Lagrangian is symmetric, and that's D, constant displacement. So we get that the momentum is conserved. Now let's suppose that the Lagrangian is unchanged when you rotate the system by an angle theta. Well, a right-handed rotation about the axis theta by theta radians, where by theta I mean the absolute value of the 3-vector theta, induces changes in the ith coordinate equal to theta cross Ri. Okay, so these are the changes then, the symmetry changes. And so what is the thing that's conserved? Well, the thing that's conserved is J dot theta, and I've rewritten this a little bit. J here is R cross P dotted into theta, and so I've, you can massage the dot cross product. So after the massage, we get PI dotted into theta cross RI, and I guess I massage it again, and I probably would have been better with the beginning. We then get R cross P, that's angular momentum, dotted into theta. This is the thing then that's conserved. Okay, so what you have then is that angular momentum is conserved when the Lagrangian is unchanged under rotations. And I'm just wondering whether this might be a typo in 7180, so I will check that. We have 3 minutes left. I guess this is sort of simple. Suppose the functions P and Q are homogeneous of degree n. Then we can change variables from x, y to x and y of x. And this y is going to be xv of x. So dy is x dv plus v dx. And then this original differential equation is p of x and y dx plus q of x and y in the sense of xv times dy, and dy is that. So now, since p and q are homogeneous of degree n, this thing is x, this thing has to be x to the n, p of 1 in v, and this has to be x to the n, q of 1 in v. And we've chosen them to be of the same degree of homogeneity, so we can cancel the x to the n. And then this gives us this differential equation, which we can integrate to that. So an example, suppose this is our differential equation. Then we have p is x squared minus y squared, q is 2xy. These are both homogeneous of degree 2. And so making the substitution y of x equals x of v times x, we get x squared times 1 minus v squared dx plus 2xv, and now dy is v dx plus x dv. And the x squareds cancel out, and we're left with this expression, which we can then rewrite and integrate, and we get this expression. That's log of x plus log of 1 plus v is log of c, and then you can then massage that, and you get that you find v, and once you find v, well, let's see, what was v squared? V is y over x, so this is y squared over x squared. And so multiplying both sides by x squared, or by x, I should say, we get this equation and solve it for that. So that's well, we're out of time, but that's that example. Okay, so is there some last minute question or comment? Okay, if not, I'm going to end the session then and end the recording. So I'll see you tomorrow at 5:30, and we can discuss homework and we can do more examples. And so it would be really useful if someone would say that certain examples might be more desirable than other examples. So if you can do that, that would be grateful. Okay, so I'm going to